Let's talk about a couple properties of logarithms. First, if you do not have an identified base, it's implied to be 10. So in an example where it says log 100 equals 2, it's really saying 10 raised to the second power is 100. There's an implied base of 10. So when you don't have a base that's written, it's 10. Second, if you have something that is log base e, that is known as a natural logarithm. And it'll take the form of this. It'll say natural log. Usually they don't have the base then. So to say ln of x equals 5 or whatever. So if you see the ln, natural log, some people call that ln, the ln of x is 5, it means log base e. It's just a log base e. So it's just really some notation stuff that you want to be aware of there for section 1. I don't think you're going to see much with the homework regarding that, but you should be aware that that does exist. And then we've got some other properties of logarithms. These are the ones that we really want to focus on. If you have a log, let's say base x, of ab, you can take that argument and you are allowed to split this and say log base x a plus log base x b. You can take this multiplication of your argument and actually add the two pieces. So log base x plus log base a plus log base x b. You can add those two components. Now specifically, if I told you that I had a log, let's say base 3 of 6, that's equivalent to saying log base 3, say 2, plus log base 3 of 3, meaning that 2 times 3 is 6. As long as those bases are the same, those arguments, when added, can be multiplied to create a larger argument and a simplified logarithm. Let's continue with this. So we've got a second concept then. It says if you're dividing them, well, it kind of makes sense here. If I'm multiplying, I add. If I'm dividing, what do you think I would do? I'll subtract. Numerator minus denominator. So you could say log base x of a minus log base x of b. Example of this. Let's say I had log base 5 of, I don't know, 27 halves. We could say that that is equivalent to log base 5 of 27 minus log base 5 of 2. If you were to put this in the calculator, it's equivalent to that. If you're just trying to simplify an expression, you could say 27 divided by 2. So you just take these arguments and you can divide and condense this down into that statement. Now we have yet another one. I tried to write these beforehand. It backfires a little bit. You can see how this is all kind of squeezing together. I think I'm going to grab another piece of paper. Let me rewrite this. So I've got a log base x a to the p. It basically says that if you have an exponent on your argument, you can transfer that exponent into a multiplication. It becomes a scalar. This is equivalent to saying p power times log base x of a. And it kind of makes sense if you think about it. Let me go back here for a second. Real simple one. This log base 10 of 100 equals 2. If I do this, log base 10, you agree that 100 is 10 squared, right? This is saying that I could take that 2 and put it in front. So I got 2 log base 10 of 10 equals 2. And if you focus on the log base 10 part of this, let me just come outside here for a second. If I was just working with that, wouldn't that be log base 10, 10? 10 raised to what power is 10? 1, right? So I could replace all this just with a 1, and 2 times 1 is 2. And you could do that with anything. You could raise this to the 3rd, to the 5th, to the 19th. Whatever it's raised to would be what this is. And so that rule really makes sense, because it's just saying that if you pull that power out, make it a scalar, it's going to be your exponent, which is over here anyways. You already knew that from the basic structure of a logarithm. And so we've got this rule that says, I'll just do another example of this, log base 5 of 7 squared. If I just had that, nothing else, this is equivalent to me saying 2 times log base 5 of 7. Those are equivalent statements. That helps if you can see it, huh? So I had log base 5 of 7 squared is equal to 2 log base 5 of 7. It's just saying that you can take that power out and turn it into a scalar. These are equivalent statements. Those are equivalent statements. Alright, so now what can we do with this? Let's look at a couple examples how we're going to simplify it. And so we'll start off with a problem like this. It says, we'll call this example 1 here. 2 log base 3 10 minus log base 3 of 4. And what they want us to do is combine this and condense this, turn it into just one log. Using those properties that I just explained, we can look at this as a scalar and we can work backwards. We can say, well, wait a second, that can become a 10 squared. So I could write this as log base 3 of 100, because 10 squared would be 100, minus log base 3 of 4. Because the bases are the same, a subtraction would imply that I could actually divide. So that means that I could write this as log base 3 of 100 divided by 4. But 100 divided by 4, that could be simplified, and I could just call this log base 3 of 25. That's me simplifying that expression. And that's really all you have to do. You just condense it. Take a big long statement that has a bunch of logs in it and condense it down to where you could have just one simple log, and it's reduced as far as you can take it. Let's do a second example of this. Maybe we have something like 4 log base 5 x minus log base 5 y plus log base 5 z. What would that become? So as we look at this problem, we see that we have a multiplier, a scalar. Anytime you see a scalar, it can become an exponent. So I can call this log base 5 of x to the 4th minus log base 5 y plus log base 5 z. The subtraction, and you do want to go from left to right, the subtraction implies that I could divide these two things. So this could become log base 5 of x to the 4th over y plus log base 5 z. But an addition means that I can take the two arguments and I can multiply them. So to condense this all the way down, I can say this is equivalent to log base 5 of x to the 4th over y times z. Now you can put the z here, or you can put it upstairs. Either one would be equally correct. And so that's a second example. I guess I didn't label it. Example 2. Second example of how you can use properties of logarithms to condense longer logarithmic statements. We'll do a couple more here. How about I do this? How about I say three log base b. We'll just call it b. We'll keep it generic. Of 4 plus log base b of 2 minus log base b of 10. And we just want to simplify that. So, this is example 3. I would start with this scalar and say, oh, well, this would be 4 to the third power. So I've got log base b of 4 to the third plus log base b squared minus log base b of 10. Now 4 to the third. 4 times 4 is 16, and 16 times 4 is 64. So this becomes log base b of 64 plus log base b of 2 minus log base b of 10. As you start to do a couple of these, it becomes pretty simple. In fact, you can do a lot of this in your head as you get better at it. The addition of logs means you multiply the arguments. So 2 times 64 will be 128. I can call this log base b of 128 minus log base b of 10. The subtraction of logs means that we can divide the arguments. So this becomes 128 divided by 10. Log base b, 128 divided by 10. Or 12, if you want to call it 12.8, that'd be fine too. And so that's another example of how you can break the logs down using your properties and identities. Now you do want to be careful. I'm going to use an example out of a worksheet here. Don't get suckered into misunderstanding this addition. This addition stands alone, and it's the two arguments that are being added together, which means that they can be multiplied. And that's what I was doing here. So watch this. If I go to like a more algebraic example, we'll call it example 4. Log base b of 2x minus 1 plus log base b of, say, 5 equals log base b of, I don't know, let's go 12. Let's see what that does for us. So the way that this is set up, because it's an addition, I can actually multiply this. Now I'd have to take the 5 times that. I'm multiplying the arguments. And so this would become log base b of 10x minus 5, as I distributed that 5 across there, equals log base b of 12. Now there's a rule that says if you have log base b, that the arguments have to be the same when you have an equals like this. So this, where my finger is, has to be equal to where the pen tip is. These have to be equivalent. So I can actually drop out my logs and just turn this into a straight algebra problem. 10x minus 5 equals 12. Bring the 5 over. 10x is equal to 17, because 12 plus 5 is 17. Divide by 10. And I could figure that x is 1 7/10. So you can get to this point where you can actually do a little bit of algebra. I don't think the worksheet's going to be that terribly difficult. If you follow these 4 examples and you look at those properties that we discussed, I think you'll do just fine understanding how to simplify logarithms using your properties. And so we've got 4 examples of properties of logarithms.